Today we commence the last topic for this course, namely complex manifolds. As we'll see, complex manifolds are closely related to symplectic manifolds. And the final example that we'll cover in this course, namely quantum mechanics, of the dynamics of the Schrödinger equation on Hilbert space, will have something to do with complex manifolds, as we'll see. Now, I'm going to define complex manifolds in a similar sequence of steps as to how I define symplectic manifolds. And we're going to commence by looking at tangent space, or even before that at vector spaces, working out what we mean by a complex structure on a vector space, extending that to a tangent space, and then finally finding a definition for what a complex manifold should be. So let's first look at vector spaces and what it means for a vector space to be complex, whatever that might mean. It's kind of clear what a complex vector space is. It's a vector space over the complex numbers. But what is it that really characterizes such vector spaces? Well, it turns out we have we're going to take away one abstract feature of complex vector spaces, and then we're going to use that to define what it means for a vector space to have a complex structure. So it could be that you have manifestly a complex vector space. You just have some vector space that you like, and it's over the complex numbers, done, right? But it might be that you have a real vector space, which is, say, even dimensional, and then you might think, well, sure, this is an even-dimensional real vector space, but maybe it's secretly a complex vector space in disguise. How would you tell? Right? How would you know if a real vector space was secretly a complex vector space? Well, I'll give one possible answer to that question. A vector space would be like a complex vector space if it had something like the number I acting on it. The imaginary number I. And how does the imaginary number I act on a complex vector space? Well, it's a linear map, right? So we're going to look for a linear map J, call it J instead of I. And the defining feature of the imaginary number I is that if you square it, you get -1. So if you could find an operator which squared to -1, then that's, pretty similar to how the imaginary the imaginary number I acts. That's the definition we're going to go with. We say that a vector space, in this case over the real numbers, or otherwise, has a complex structure if you can find a linear map J, such that when you square J, you get minus the identity. And then, from now on, we'll think of J as the imaginary number I, square root of -1. So we'll diagonalize J and we'll work in that basis of J, where J looks like square root of -1. So let's just check that this definition isn't completely ridiculous. So for the example where we really do have a complex vector space, it had better be the case that if J is meant to be like square root of -1, then it better be like square root of -1, right? So then that indeed satisfies the requirement to be a complex structure. If you square J, you get -1. So all is well. Now, that's the case, that's what it means for a vector space to be complex from now on in this course. What we're going to do now is see how complex vector spaces interact with symplectic vector spaces. There's a lot of similarities between these two linear spaces. Let's try and capture a notion of compatibility between these two types of space. All right, well, here's step one. Let's start with a symplectic vector space and then see if we can simultaneously put a complex structure on this vector space. Well, we want to have, to be able to put a complex structure on a symplectic vector space, well, you can do it, right? They can do them completely independently of each other. You could have some symplectic form, some complex structure, and it might be they have nothing to do with each other. But what we would prefer is that these notions coincide, and so we have to come up with an idea of what it means play nicely together, and this is what we're going to do now in this definition. And here's the play nicely condition. So the play nicely condition is, if you take the symplectic form and you build this new bilinear form using the complex structure, then this thing here is an inner product. That's what it means for these two structures to play nicely with each other. It's a definition. And that in particular means J is compatible with omega if and only if so there's a little exercise that this is an if and only if. So this tells us, if you like, multiplying by I doesn't change the symplectic form, and that multiplying a vector by I undoes, if you like, the symplectic form, turns it into a positive form. This is a bit abstract. We'll take a look at an example and then you'll see exactly where all of this comes from. So let's take R to the 2n. This is our vector space V. And we'll take the bilinear form symplectic standard basis. So we know that by the symplectic Gram-Schmidt process, we can always write a symplectic form in matrix form like that. And then you see that J, what on earth is J? Well, J is just this matrix here. J squared is a very nice property. It's minus the identity. So it's a complex structure. And if you stick J here, it squares to minus the identity. Okay, this example might make you optimistic that this is not just a miracle of this very simple example, but maybe there's something more general here. And we already know, right, that thanks to the Gram-Schmidt process, that every symplectic vector space has a nice symplectic orthogonal basis, and you could always then imagine defining J using that basis. So let's see if indeed that's correct, and indeed it is. So if you have any symplectic vector space now, then you can always find a complex structure which is compatible. So I'm not going to do the full proof of this proposition, I'll just do the existence. This example here essentially makes it clear how to do it. If you have a symplectic vector space, then there is a compatible complex structure J on V. How do you build it? Well, just find firstly a symplectic basis. There always exists one. And then define J just like that. J on E gives you F, J on F gives you minus E. So if you square J, you get minus the identity. So that's a complex structure, and it's certainly compatible with the symplectic form. sorry. Hang on. Forget what I just did. So, that's what it means now for a vector space to be symplectic or complex or compatible. So if you like, we've already defined complex manifolds, but in this ultra-local neighborhood around a point, so namely on tangent space. Let's extend this definition now to apply to manifolds, so everywhere on a manifold. And the way we're going to do it is we extend the definition we just made on vector spaces to work on tangent space, but for all tangent spaces. And then you have just an additional requirement that things are smooth. So what do we need to make a complex structure, or an almost complex structure on a manifold? Well, we need a smooth, now, field of complex structures. On tangent spaces. And what that means is it's an assignment for every point in this manifold, there is a complex structure on tangent space Jx. And this operator squares to minus the identity. And if you have such a thing, then we say that we have an almost complex manifold. So why do we say almost? Well, I mean, sort of clearly implies that there exist almost complex manifolds that aren't, in some sense, to be made precise in the future, that they aren't complex manifolds. So we're going to have a separate definition of what is a true complex manifold, and it will have additional requirements. And so there are obstructions to turning an almost complex manifold into a complex manifold to do with extending this Jx all the way over the manifold. Now, just as for vector spaces, we had this notion that a complex structure could be compatible with a symplectic structure, we can extend exactly that notion to manifolds. So suppose we have a symplectic manifold. And it's exactly this local definition, but extended to apply to every tangent space of the manifold. So an almost complex structure is said to be compatible if for every x in the manifold we have this assignment of a positive bilinear form to each on tangent space just as we did for the vector space case. And what do we call a positive bilinear form on tangent space? Well, we call it a Riemannian metric. So there's three things here on tangent space when we have a compatible complex structure. You have the symplectic form, which is this non-degenerate 2 form. You have an almost complex structure, which is another kind of object. It takes a tangent vector and gives you a tangent vector. And we have a Riemannian metric, and these three things have to play nicely together in exactly that way. They're to be called compatible. I mean, it's perfectly legitimate to have incompatible structures, but this gives us some additional benefits when they're compatible, because we get this Riemannian metric for free, right? If we have a complex structure that's compatible with a symplectic structure, now we know there's a Riemann metric on this manifold. And Riemannian metrics are like super great, right? You can do all kinds of cool things with them. You can talk about parallel transport and curvature and so for those reasons, compatible, almost complex structures are very, very, not only simple but sort of elegant objects. Now, just as for the vector space case, you might wonder if you have a symplectic structure, maybe you get an almost complex structure for free. Indeed, you do. It's exactly the same argument. I'm not going to do the proof of this proposition, although I hope you can imagine how it might go. So the particular instance that we're going to take is that we suppose we have a symplectic manifold with a Riemannian metric, then that gives us a canonical complex structure J on M. We could have taken different pairs, but this is the one we're going to go with today. Because the other implications are fairly obvious. If you have a symplectic manifold with a compatible almost complex structure, then you have a Riemannian metric. That's just the definition. And if you have a Riemann metric and a complex structure, then you get a symplectic manifold as well. So the proof is omitted for that. Instead, we'll focus on examples to illustrate the results, and we'll take again the simplest example possible, which is phase space for a mechanical system. M is r to the 2n, and we'll have standard symplectic 2 form that we've been taking throughout this course. And then we're also going to take as our, we need a Riemannian metric, and the one that we're going to take is the standard Euclidean inner product. And then we're going to define the following almost complex structure. So we need some map that takes a tangent vector, gives you another tangent vector, and squares to minus the identity. Take this one. And with respect to this basis here, to these coordinates here, Zj, we'll see that J corresponds exactly to multiplying by square root of minus 1. Also, we have since we have a basis here for tangent space, we can express our almost complex structure in terms of that basis. So that's one notion of what it means to be complex. You take some manifold, you find an almost complex structure on it, and then you can say that the manifold is almost complex. But there's a completely different way you could define complex manifold. And we might hope that one is at least a subset of the other. So let's take approach 2 to defining what it means for a manifold to be complex. In approach 2, we say a manifold is complex if it looks locally like a complex vector space. Excuse me, like the complex numbers. So this is the more traditional differential geometry definition. What's a manifold? Well, it's something with open sets which are locally homeomorphic to Euclidean space. Well, we're going to replace that with complex space. So what is a complex manifold? Well, it's a set, right? Locally complex space, I guess you call it, instead of a locally Euclidean space. And so instead of having an atlas of charts that look locally like Euclidean space, now we have an atlas of charts that look locally like complex. So we have this complex atlas. So I've got to tell you, what is that? What does that even mean? Well, firstly, M is covered by these sets U alpha. V alpha are open subsets of C to the N. And U alpha locally looks like V alpha. So we've got to express that with these maps here, these coordinate maps. And just as we did for manifolds, we need that these maps are compatible with each other. If you decide to represent points in your manifold with some coordinate system on one day and then on a different coordinate system on the other day, it better be that everything's compatible. And let's say what it means, compatible. Well, it means that this overlap function, psi alpha beta, they have to be nice, right? And what does nice mean? Well, firstly, we need that these maps are bijections, phi alpha. And we need that these overlap maps are holomorphic. And I'm going to go ahead and guess that you don't remember how to define a holomorphic map of n complex variables, so I'll do that in the next. So the first thing to remember as I'm erasing the board is that a complex function is differentiable if and only if it satisfies the Cauchy-Riemann equations. So start by remembering that. In one complex variable. Now we have many complex variables. So we need to generalize that notion slightly. So what does it mean, holomorphic, if you have a function of many complex variables going to many complex variables? Well, let's deal first with the case where you've got a function that goes from m complex variables to 1. So if you separate f into real and imaginary parts, then this function is holomorphic if it satisfies the many variable Cauchy-Riemann equations, which read df dx mu equals df1 dx mu equals df2 dy mu and df2 dx mu equals minus df1 dy mu. Oh, I didn't write down that z is x plus y. I'll do it again. Sorry, it's not upper indices. So a map from many complex variables to 1 is holomorphic if it satisfies the Cauchy-Riemann equations. And when you have a map from one complex variable to 1, then you see indeed that that smoothly deforms to that notion of holomorphicity that you should be familiar with. And then if you have a many variable map, well, you just write out the vector of these functions and you ensure that each component function is holomorphic. All right, so that's what it means holomorphic. It means complex differentiable in each variable. And that's what it means complex manifold. So it's a manifold which locally looks like c to the power n. And we don't have to say the word smooth because holomorphicity is a very strong constraint already by itself. All right, so what does complex manifolds, as written here, have to do with almost complex manifolds? So the word almost suggests that any complex manifold should at least be an almost complex manifold. That should be the case, right? Otherwise, the definitions are totally crazy and we shouldn't have used that language. It would have been an unethical definition. So that's right, it is the case. Every complex manifold is at least almost complex. Well, it's better than that. It has a canonical almost complex structure. And the proof idea, I mean, it's a bit longer than what I'm about to write, but you just define on tangent space the following linear map. I mean, you have the coordinates d dxj at your disposal. And you have the coordinates d dyj at your disposal. So you just define on tangent space that linear operator. So if you like this definition here, we're defining a manifold to be a complex manifold if it's an even dimensional manifold with all this extra structure on it. So you immediately write the complex numbers in terms of real and imaginary parts. And then you interpret all the constraints for holomorphicity in terms of these real and imaginary parts, and you come up with all these intricate constraints on these functions, these transition functions. You can always do that, right? You can always do complex analysis in terms of real and imaginary parts. But like at some point, I don't advise it because it misses all the elegance of complex analysis. And all the results are exactly true if you never ever write down a complex coordinate, as long as you focus on real and imaginary parts and insist on splitting every complex equation into real and imaginary parts. You can do it, right? But it misses the beauty of complex analysis. And so what we're going to do now is transition from this real and imaginary part way of thinking about complex numbers to the complex variable way of thinking about complex numbers, where you have complex coordinates, z, which are just complex numbers rather than being thought of as two component objects. And when you do that, you come to this most confusing part of complex analysis, namely you think about one complex variable, you have the complex variable z, but that's not enough coordinates depending on the kinds of operations that you're going to do in complex analysis. So you introduce z complex conjugate, so you can get at the real and imaginary parts by adding z to its complex conjugate. Now the thing that confuses people in complex analysis is when you say, let z and z bar be independent complex variables. Complex analysis, and then what you're doing there, this is something that often happens, right? Like z and z bar be independent variables. And people go around treating z and z bar as though they're completely independent variables, and they can derive all kinds of interesting things by doing that. And you're only really doing complex analysis when you restrict to the real subspace, namely z equals what am I going to say? Z plus z bar is real. So we're going to do exactly that. We're going to now introduce complex coordinates for all our manipulations, and we're going to think of z and z bar as being completely independent complex variables. And then only when necessary do we restrict to the real subspace. It's extremely convenient to have complex coordinates which are independent, z and z bar, because it allows us to express the constraint of holomorphicity in a very, very nice way. We learn that a holomorphic function is one that only takes z's to z's and z bars to z bars. Extremely useful in simplifying a lot of our arguments. So on our way to building complex coordinates z and z bar, well, we need to assemble together real and imaginary parts. So let's look at our favorite our favorite complex manifold with complex dimension n. N here. And then we'll start by looking at tangent space to M. So tangent space to M is just this sort of linear span of the real and imaginary parts. Simple enough, right? And also, we have a similar basis for the dual space. Like that. We have a dual basis. Yep, question?
Complex linear coefficients or real?
This is real. We're going to do everything with real coefficients here. It's the span over R, right? And then you have to keep track of what it means to be a real and imaginary part, which means putting in minus signs when you do certain operations. So that's awkward. We don't like doing that because we know we can express things more elegantly in terms of complex coordinates. That's exactly what we're going to do now. We're going to form linear combinations, complex linear combinations of these otherwise real vectors and introduce a new basis analogous to z and z bar. So where do these complex coordinates, these real and imaginary parts come from? Well, if you find a chart and the coordinates of P are exactly real plus imaginary parts like that. Now we get to do now we start defining our analogues of these complex coordinates on tangent space. And we'll see that we're forced to do something impossible, at least with regards to this real vector space here. So I'm going to define the following vectors. They no longer live in this tangent space. They can't possibly be living in here because that's a real vector space. They live not in the tangent space, which is a real vector space, but it's complexification. So you take a vector space and you just formally turn the coefficients into complex numbers. That's all we're doing here. So what we're doing here is we're saying that Z and Z bar, now just as for the original single variable complex analysis case, Z and Z bar are now independent complex variables. That's roughly what we're saying here by complexifying the tangent space. Oh, that tensor product is not over C, that tensor product is over R. You'll get into a world of trouble if you put that over C. We note something, right? The complex conjugation operation, the standard one, has a nice effect on this basis vector here. It simply turns it into the corresponding basis vector ddz bar. Now we have a complex vector space here. We also have its dual complex vector space. We just complexify that as well. And we're able to extend the almost complex structure as well to this bigger vector space. And we have this J map, right? And the way you have it act is you just act on the first tensor product factor. But this allows us to express J now as a element, as a tensor of degree 1, 1. And it eats a vector and gives you a vector. So you can express J as a linear combination of tensor products of 1 forms and vectors.
One question.
Yep.
We have, so if I have this clear, we have a priori two different complex structures. The canonical one on C.
We have the canonical, a priori 2 complex structures,
Yes.
one on C, yes.
To define this complexification.
Yes.
And then.
And then we have this other thing, J, here.
And we set it up so they are kind of equal.
Yeah.
Okay.
We set it up so they're compatible here, except. Now J, what it allows us to do is to break up this complexified tangent space into 2 subspaces. The subspace which have eigenvalues, now I've written, hang on. The subspace corresponding to eigenvalue minus square root of minus 1, and the subspace corresponding to eigenvalue minus square root of minus 1. Yep. And
Sorry, I have a little problem with the fact that it seems to be that J is real.
it seems to be that J is real.
Because if you take the complex conjugate, you will get the same.
So in the eigenbasis, J has eigenvalues square root minus 1 and minus square root 1. So what does it mean real actually for you?
Yeah, real is if you take the complex conjugate of J, J comes back.
Yes.
But for I, it's not the case.
So complex conjugate is a basis dependent notion. Yeah, so if you change a basis in a vector space and you do a complex conjugate, it's not the same thing. So that's why it's sort of, one tends to avoid saying the words complex conjugate. One tries to avoid saying as though it's an invariant concept. I mean, you want to do it, it's a useful thing, it's just don't think that it's unitarily invariant. So we can break up this 2n-dimensional complex vector space into 2 subspaces. And we're going to give these subspaces, elements of these subspaces, special names. I'm going to call this one holomorphic and this one anti-holomorphic. So it's worth checking that the eigenspace of holomorphic tangent vectors is indeed just the span of the basis vectors d, d, z, j.
One more question.
Yep.
The DZJs, we
D,
defined
Z,
there.
yes,
Yeah, they're still there. Are they now complex linear functionals?
they are now complex linear functionals, yeah.
Do we see this by this construction? Because it feels like we did the same construction, like parallelly, but independent of one another in the other space.
So in order to talk about DZJs, we need a pairing between,
And so we just define it
just
like,
define,
like J, okay.
yeah, just like J, yeah. Okay, so if we have now a vector field, so this is just talking about vectors at a point in tangent space. So we have a vector field now on our complexified tangent space. Then what this allows us to do is we can decompose this vector field into holomorphic and anti-holomorphic components. And the reason we're doing all of this is to build up all the tools we need to do differential geometry on these complex manifolds in terms of these coordinates dz, well, z and ddz and dz. In particular, we're going to need at least to be able to talk about two forms, right? Because if we're doing symplectic geometry, well, you need a two form at some point. So we want to look at the space of complex forms now, which are dual to tangent vectors, complexified tangent vectors. And we want to talk about higher order complex forms as well. So we need to build them somehow, so let's do it. Here's the definition. The vector space of complex Q forms at P, at a point P in the manifold, is none other than the space of Q forms, but just complexified. You allow coefficients to be complex numbers now. And now we're going to try and build bases for this space and decompose a general form in terms of this basis. So you have a complex Q form, so you can write it in terms of like real, real and imaginary parts, right? That's what complexification means. Oh, there should be a P here. We're doing things at P. So you can always write a complex Q form as a linear combination of two Q forms, real and imaginary parts. Another operation we need to extend to this complex realm is the exterior derivative notion. You just do what you think you would do. Just try the simplest definition possible, which is do the normal exterior derivative but on the real and imaginary components, and make it a real operator so that it passes by I without complex conjugation. Well, that means that indeed D is a real operator, so that when you take complex conjugations in this particular basis, you don't get a different linear operator. Let's check that the familiar properties of two forms and wedge products still carry over. It's an exercise here. So you can check that this definition here does play with complex forms in exactly the way you'd hope that they do. So this definition here has the same defect, if you like, as the other definition, namely we haven't expressed it in terms of our z and z bar coordinates yet. Let's rectify that and come up with a basis now for the space of complex Q forms. So we're going to just restrict to manifolds where we've given ourselves this decomposition of the complex tangent space into holomorphic and anti-holomorphic parts. So where we have this, define this almost complex structure J. And we'll have now a rather lengthy definition. So now we start with an m-dimensional complex manifold, and we're going to try and understand this complexified Q-form space here. And we'll see that there's a little bit of internal structure that we can extract. So we suppose we have ourselves a complex Q-form. So it's some combination of real and imaginary parts. And further, we assume we have some integers, R and S, non-negative integers. I will reveal this. R plus S equals Q. And now we're going to isolate special forms, special antilinear functions of Q vectors. And we're going to isolate them by supposing that their arguments, namely a bunch of vectors here, are either holomorphic or anti-holomorphic. And then we're going to demand a condition. And here's the condition we're going to demand. If, when you substitute these vectors into the argument of your favorite complex Q form, you get 0 unless R of these Vj's are in holomorphic and S are anti-holomorphic, then if you have such a special form like that, that it's exactly 0 unless R of these vectors are holomorphic and R are not, and S are anti-holomorphic, if you've got such a form, we're going to call this a form of bi-degree R comma S. So obviously, a Q form with bi-degree R comma S is a Q form, is a complex Q form, but not the other way around, right? We've isolated subspaces of this vector space. And we'll denote the set of RS forms at P, it's obviously a subspace of the set of all complex Q forms, as omega R comma SP at M. This is just a sort of lengthy way to carry out some linear algebra. If you remember, Q forms are elements of the vector space, the antisymmetric vector space, which is the tensor product of tangent space Q times. So it's the antisymmetric subspace of the Q-fold tensor product of V. Now, what we're doing up here is we're observing that when V has this direct substructure, when V is the direct sum of two subspaces, as is the case in the complex case, and you put that in here, and then you realize that the direct sum distributes over the tensor product, then you can get a different decomposition here. There's two ways of writing exactly this vector space. So when you take the tensor products of direct sums and then you distribute the direct sum over the tensor product, you can equivalently express this vector space as the direct sum of tensor products, but where you've got R components in the first subspace and S components in the second subspace. So that's the linear algebra explanation for this lengthy definition in words. Okay, a smooth if you have a smooth assignment of an RS form on at TPM for all P, sorry, it's omega, isn't it? Omega Q RS P for all P, then we call that an RS form over M. And we denoted just omega RS M. Now let's take a look at our RS forms in a chart. So once we have a coordinate chart, we can form some differential forms, with taking exterior derivatives of the coordinates, for example. And then we can classify the bidegrees of these forms. So dzj has bidegree 1, 0 because it lives in the dual of the holomorphic vectors. Similarly, dz bar j has bidegree 0, 1. And something that we'll see later on, this form here has bidegree 1, 1. Very interesting to form that one. And if you have a generic form of bidegree omega rs, of bidegree rs, then you can express it in terms of wedge products of these basis forms. Always write it in terms of this particular basis here. Oh, there's a sum that's missing. Sum over the j's and the k's. And this is that's a basis for omega rsm, and the one explanation is this linear algebra argument that I gave just there. And we'll end with a proposition that collects up some properties of these complex differential forms. So we suppose we have a complex manifold of complex dimension M. Then here's some properties that are very interesting to just collect together. So if you have an RS form, a complex Q form of bi-degree RS, then its complex conjugate is just reverses these R and S's. It's kind of clear from the basis expansion. And if you have two such forms, perhaps of differing bi-degrees, and then you wedge them together, well, that's in R plus R prime, S plus S prime. And finally is the decomposition that I've already alluded to. You can always express a complex Q form as a linear combination of forms with bi-degree RS. I mean, your generic complex Q form won't have a bi-degree. It's a generic one, will be a linear combination of all kinds of forms of differing bi-degree, but you can separate out its components like this, and this is unique. And if you like, we could summarize the observation we made just before, that the complex Q forms of M breaks up into this direct sum like that. So we've just had a whirlwind tour of complex manifolds, manifolds which are locally like the complex numbers. And we've introduced a bunch of substructure to the space of differential forms on these manifolds. So in the final lecture, we're going to look at the symplectic structure of these complex manifolds. We're going to take some key examples and look at Hamiltonian actions on these complex spaces, and we'll see that there's some very interesting Hamiltonian actions that you can write down. But for now, I thank you very much.